Let's look at this example to see how this stuff all works. So suppose C1 is the arc of the parabola blah traced from -5, -3 to 0, 2. So let's draw this out. So 1, 2, 3, 4, 5, and 1, 2, 3. So this is -5, -3. And then 0, comma, 1, 2. Okay. So I'm going to trace out this parabola. And how far does it go in the, notice that this is x equals 4y, 4 minus y squared. And it starts here, and it ends there. A few more points to draw might be helpful. Notice that when x equals, if I set x equals to 0, I get 4 minus y squared, which gives me y equals plus or minus 2. So when y is minus 2 over here, I'm crossing the x-axis. When y is plus 2 over here, I'm crossing the I'm crossing the y-axis, x equals 0. So these are also points on my parabola. I can also think about what if y is 0. Then I get x equals 4. So 1, 2, 3, 4. So now we can kind of see the parabola emerging. So it goes like that. And again, it's traced out in that direction. How do I know that? I'm inferring that information by the fact that it says traced from to. So that's one way that you would know the direction. Okay, so now I've drawn my curve, and the next step is to parameterize it. Various ways to do this. Again, I'm going to stick to using t. We don't have to. We could use some other parameter, or we could just use the natural parameter, if you will. X is written in terms of y. We could use y as a parameter, but I'm going to stick to t's. And how am I going to parameterize this? Well, so taking the cue from the fact that one variable is already solved in terms of the other, I'm going to let x, I'm going to choose y to be t, and then x is going to be 4 minus t squared. And again, if I substitute that in there, I get x equals 4 minus y squared. Check, since that is the curve that I'm given. So I have my parameterization, and then we are going to need not the big square root thing that we were talking about in the previous lesson, dx dt squared plus dy dt squared, because we're not doing a line integral with respect to arc length. We're doing a line integral with respect to dx first, and then with respect to dy. So I am going to need information about, going back up here, information in the first integral, I'm going to need x prime. In the second integral, I'm going to need y prime. So I'm going to calculate that here. So x prime of t is minus 2t, and then y prime of t is 1. So then I'm going to go here, and this is going to be the integral of y squared, which is t squared, times dx, which is what's being converted to x prime of t dt. So that's minus 2t dt. And then plus x, which is 4 minus t squared, times dy. dy is what's getting converted to y prime of t dt. Y prime is 1, and then dt. And then I got to figure out what t ranges from. Okay, so t here is equal to y. So if I look at my bounds for y, then I can figure out what my bounds for t are. They'll be the same. Notice that y starts over here at the point -5, -3. Excuse me, so that is the lowest bound for t. And then goes all the way up here to the point y equals, to the location y equals 2. So that is my upper bound for t. So I'm integrating from -3 to 2. Those are my bounds for t. And then I'm just going to clean this up a little bit and then talk some more about line integral. So I get minus 2t cubed dt plus 4 minus t squared dt. And at this point, we really do kind of combine them into the same integral, and we don't have these two rogue dt's floating around. So I get minus 2t cubed minus t squared plus 4 dt. Once again, we've arrived at a single variable integral. This one is just a polynomial integrand, so we can definitely integrate this using single variable calculus techniques. So I will let you fill in the details and verify that you end up with, in a mixed fraction form here, 40 and 5/6, or if we put it into the normal fraction, non-mixed fraction, this is 245/6.